All right, thank you for your patience. This part of the workshop is we're gonna do some live coding on observable. If you want, you can go to this link. I believe it's also posted in the Slack channel of the event. And just want to give some high-level view of why you want to write your own custom layer. deck.gl try to provide a catalog of useful layers out of the box, so you could just import them, set all the props according to documentation, and all of these layers are written what we call compliant, so it will work in geospatial, non-geospatial, in all sorts of coordinate systems, and has the correct interface. But you know, they don't cover every visualization scenario that you will need. So if you are doing something that's you have a lot of ideas about how visually this thing should be presented, you probably want to do something more creative than something you would regularly see online. Or if you're dealing with very complex data, you will probably have your own data protocol, your own data format, and your own way of communicating with the server. And in that case, the basic use case where you just pass an URL to the data prop probably is not going to cover what you're trying to do. And in all of the above scenarios, writing your own custom layer is a great opportunity for you to capture all the code that is related to a part of your visualization and encapsulate them in a single class. And then in the rest of your application, you could just reference this layer just as any other official layer from deck.gl catalog, and set some simple props, and things are good to go. There are several ways to write your own layer. We have a lot of articles on the documentation site for this, and we'll start from the first one, that is writing your own composite layer. So if you're familiar with a little bit of the deck.gl core system, we have two types of layers. We have primitive layer, which directly draw content to the WebGL context. And then we have composite layer. Composite layer renders other layers instead of drawing their own pixels. And composite layer is a great way to handle stuff such as you have a highly custom data format. You have to do some pre-processing before you want to hand this data to the standard base layers, basic layer types for them to render, or just you have some weird stuff you need to load, like you have asynchronous assets you have to dynamically request from your server, and these are cases if you just you know, without using a custom layer, you will have a lot of loose code of data processing callbacks, accessor callbacks that is floating around in your application. And if you have like, I don't know, a few dozen of layers, it quickly gets out of control in terms of code management. For this example, I am using a data set that describes the submarine cables that connect all the continents. As a very fun data set. There's no base map here, but you can clearly see, you know, where things are happening. And if you examine the data, it's basically a GeoJSON, and each feature describes a particular cable that goes from one landing point to another. And I have a basic boiler template set up in this notebook. Here you can see that we're just using the stock GeoJSON layer to render this raw data. The only complexity is we have a little color parser that goes from hex string to RGB array, and it basically looks like that. So suppose we want to make this a little more fun to look at. We want to have something that's not just a plain line that renders to draw these cable lines. The way you create your own layer is simple. Here, because we're in observable, we are importing everything under the deck namespace. But in an vanilla JavaScript application, you probably just import a composite layer from deck.gl core. And here we have. So for each layer class, you have a static property called layer name. I'm going to make a hack here. Don't do that in your own app, but this hack is required in observable so that every time we reevaluate this cell, it's gonna completely rebuild that layer. So it doesn't do anything funky. And then you have an static property on the class that's called default props. Default props describes basically the props that you want this layer to accept. There is a whole article on documentation about this. It's a powerful system. It's not required that you declare something as a prop. It's still gonna see it when you access layer.props. However, if you do declare the props, Deck will have a better idea of knowing what type that prop is and will handle it accordingly. For example, if you have a prop that's a color, it's gonna be an array of 3 or 4 numbers. And if you are in a React app, whenever you re-render, you recreate a new layer instance. And if you define that color in line, JavaScript will give you a new array object. So if you do a shallow comparison between these two prop, the two state of this layer, you'll see that that color prop has changed. But if you declare in default props that this prop is a color, Deck will be smart enough to know to look into each component of that color and actually tell if that color has deeply changed, and only triggers a re-render if it does. It's the same thing for accessor functions. I'm assuming you're familiar with how layer accessors work. When you are doing an inline function, again, for every render, you're actually creating a new function instance. So you do a shallow comparison, you can see the props have changed. But deck.gl doesn't actually re-evaluate that attribute unless you tell it to with update triggers. That is an unconscious decision, so that we don't trigger very expensive CPU operations unless you really wanted to. So let's just play with this a little bit. Let's say for this composite layer of ours, we are going to accept a GeoJSON that has a bunch of line strings, and we will have an we'll have a prop. Called get color. So to use that, we're going to replace that layer where we render the cable GeoJSON with our own class, and we define a get color accessor. Yes. Oh, sorry. Let's quickly go through what a layer contains. A layer has implements a bunch of lifecycle methods that the deck core will call throughout the rendering cycle to get to the state where it's ready for drawing. We have initialized state, which sets up WebGL resources usually when the layer is first added. A layer is uniquely identified throughout its lifecycle by its ID. So the first time we see an ID, we will call initialize state for this is an opportunity for the layer to create a bunch of expensive things and store them in memory for later access. And every time you update the props or update the state of this layer, the layer will get re-evaluated by calling update state. This is where you can do a bunch of processing of the new incoming prop values and probably want to store them in layer state for use. And for primitive layers, we have a draw call that will render something to the WebGL context. And for composite layers, which is what we're dealing right now, there is a render layers method which will return basically a list of layers that are the sub layers of this parent layer. When you have a pickable layer, you hover over it, you click on it. A method called get picking info is called for an opportunity for this layer to process that incoming picking information and decide what additional information to surface to the user. And finally, the last time we see a layer ID, or you say you set the layer array to a new array that has a particular ID removed. Finalized state is called on that layer to an opportunity for the layer to clean up any resources it's holding on to. So let's just simply implement this layer by telling it to return a GeoJSON layer that will simply put that GeoJSON on screen. So we will return a GeoJSON layer where we are going to call get sublayer props. This is an helper method that is on the composite layer that will do a bunch of things for you. Basically, it takes all the core props of whatever this composite layer sees and by default pass them down to all the sublayers, for example, pickable, visible, opacity. These are the basic things, or coordinate system. These are the basic things. Usually when you have a hierarchy of layers, you just want them to all share these properties that user passed to the parent layer. And this makes it very easy for you to not think about it and just things mostly will work out of the back box. So we are going to just pass directly the data of this layer to the GeoJSON layer, and note that we have this props we defined called get color. In GeoJSON layer is called get line color. So we will just pass that. Yes. Oh, yes. That better? Oh, lost it. Oh, we need an ID. So let's say lines. All right, we didn't define the width. There we go. So so right now this layer is not very interesting. It just does what GeoJSON layer does. But because we are returning an array of layers, here we can do something more interesting. Let's add some labels to these lines. So for that, we are using Turf.js to do some GeoJSON processing. If you are not familiar with it, it is a pretty comprehensive library to handle geospatial data in GeoJSON format on the client. It is pretty cool and will come handy a lot of times when you just need to do something quick. So to do that, we will need to extract the position and some properties of these labels that we want to render from the line strings. To do that, we are going to do that in update state. So usually you want to guard this by checking if data has changed for observable, because we are manually reevaluating the cell. We don't care. So let's say we're creating a new array that contains all the information we need to draw the text labels. In Turf.js, there is a utility called segment each that will allow you to iterate through a GeoJSON without looking at its content. It will give you every line segments that's between two vertices, regardless of whether they're in polygon, multi-polygon, line string, or multi-line string. So we're going to do that. So each line segment is going to be returned as a feature. And in here, let's say, because some of the curves have very fine segments, we don't want to add so much text there that it overwhelms visually. So let's say let's get the length of the feature, and so the default length utility returns numbers in kilometers, and we only add labels for line segments that's bigger than 500 kilometers. Now we need to look into what the line segment has. We'll just take the start and end points of that line segment. So P0 and P1 will be start and end, and we can use a function in Turf.js called rump bearing to get the rotation in between these 2 points in Web Marketer. And we also want to place that label at in between these two. So we'll just take the naive midpoint between these two. So just take the average of X and Y, and with that, oh, sorry. Now let's store that in our labels array. So we have position will be the midpoint. Angle, let's just set that to bearing. See how that goes. And the text will be, if we look at that, property will be name. All right, when everything's said and done, we call this set state. That will store this labels array in the state of this layer. So whenever this layer gets updated, state is a persistent object that's retained throughout the layer's lifecycle. And you can keep putting things in there, and whenever state gets mutated, it will trigger an update of the layer. Now let's try to use that. So we will also do this. So for the text layer, we'll give it a unique ID. We'll call it labels, and data will just pass the labels array that we calculated in update state. And we'll say get text will give us, that is within the structure that we stored in labels, and get position. Because we're doing this this way, let's say get size. We will do size units of meters, so it corresponds to the width. So it will appear small when you are zoomed out and bigger when you zoom in. And just say, let's hand wave it 20 kilometers per character. All right, so it's showing something. So for each like long leg of these cables, we are having a label that's shown on there. Let's fix the rotation. That may or may not work. And we want to say get color. Let's do a fancy label. So we have a background. Oh, rotation is a little off. I think the bearing that Turf returns is from true north. Our rotation is from horizontal. So let's do a 90 minus degree. Oh, did I lose it? There you go. So so for each cable, we're seeing a color line and also a color label that describes its name. There's some weirdness of text rotation. You'll have to check if it's beyond some limit. You just rotate it 180 degrees. But it's a nice way to get things that's not in the official layer catalog capability in there. And if you look at how this will work for your own application, this will be how you use it. It's very clean, and you hide all the nasty implementation details of data processing and all the fine tuning, like rustling the angle degrees, for example, in a layer that is neatly tucked away. And you don't have to really think about it when you just want to visualize a different data set. So let's go to the next notebook in the collection. Another way of doing your custom layers is called subclassing. This is only one step away from writing your own layer from scratch. We won't have time to cover all of that in this particular workshop, but this will get you to introduce to a lot of core concepts of what happens inside of a primitive layer that directly draws to GL context. And in this one, we are going to introduce you to shader injection. So all the official deck.gl layers, the shader code are written in a way that we have built-in injection points that are basically functions that are called throughout the vertex and fragment shaders. If you want to quickly manipulate how things look like, such as color of an object or of a fragment, you don't usually have to rewrite your own shader from scratch. Instead, you just hook into one of those injection points, and they are well documented on what has been calculated and what is ready in there and what you can do with them. And you can just do some quick manipulation of the variants to make things work. So to illustrate that, we are going to mess with a scatter plot layer. So here I'm just loading some random data set that is generated into a JSON array. This is rendered with an orthographic view, so it's just 2D stuff. And to subclass the scatter plot layer, you just make a new class that extends the scatter plot layer. And instead of scatter plot layer, we're going to here render a circle layer instead. Uh-oh, did I break something? Oh, yes. All right, so now our own custom class doesn't do anything other than just do whatever the base layer does. But we can change that, and the way you do shader injection is you override a life cycle method called getShaders. And we don't have to mess with most of the things there, so let's just first return whatever the base class does. And from there, we want to do some injection. I've listed on the bottom of this page some of the injection points. You can get the full description in the documentation link that's on top of this page. But example injection points are like the declaration in your vertex shader. You can inject directly into the start and end of the main function, or you can inject into one of those deck.gl specific injection points. So for example, future size is called right before we perform projection, an opportunity for you to change the size of the geometry. If you have used the data filter extension, that's where it injects this code and check if this object's data filter value is within range. If not, then it changes the size to 0. Otherwise, it leaves the size intact. That's how it hides something. Similarly, deck.gl future color is another injection point where you can, before color is set, you can tell it to use a different color. So let's play with that. Let's just put something in the fragment shader so that we are manipulating things per pixel instead of per object. So if you look at the signature of future color, it looks like that you are passed with the color that is being proposed for this pixel, and then a fragment geometry, which contains is a structure that contains a single field that's the UV of your of this current fragment. So let's just make something simple. We are just going to rewrite color. So we'll change the R value to 1.0. So the shader colors are RGBA values in VEC4 format that each channel goes from 0 to 1. So if we do that, you can see that our points are suddenly red. So that is proof that things are working, and we can do something a little more interesting. Let's say instead of just setting everything to 1.0, we will use the smooth step function. Let's say we'll interpolate between 1 and 0. Based on how far it is from the center. Now you have an oddly 3D-ish ball that has a gradient from its center out. If you are not familiar with GLSL, I can recommend some good resources. There is this website called thebookofshaders.com. It very clearly explains all the basic concepts and functions that you can use in WebGL shaders. There's also shadertoy.com, which is a way you can play in a sandbox. You can see some stupidly crazy examples that their users have created. It's its own community. It's pretty fun. So let's try to do something a little more weird. So let's say we'll take the UV of this fragment, and we'll say if it meets a certain criteria, we will not draw this pixel at all. That's a clear Pac-Man style. Let me just take the absolute values of UV so we have something symmetrical. Now suddenly you have a shape that is now circle, and if you are adventurous enough, you can pretty much do anything with this technique. If you look at the implementation of scatter plot layer, it basically draws a quad. So it's two triangles that makes a square. And the shader is actually doing the drawing of the circle and the outline inside that by testing the UV position against all the other attributes of line width and color that you set. You could also do some different math, and suddenly you get diamonds. I've got questions on GitHub where people are trying to do a more traditional chart, scatter plot chart sort of thing, where you have to have different legends for different data types. And actually doing a subclass of scatter plot layer is a great way for you to just quickly whip up different shapes for your thing. And that would, comparing with using an icon layer where you're reading from a texture, it is much faster, and you have, vector shapes that you can zoom in as far as you want, and it's nice and sharp. All right, we're out of time, but I think just want to show you something that if you want to see something crazy that you can do. With custom layers, this is a side project that I've been working on. I will share the link to the GitHub repo. And this is basically a non-geo graph renderer. This particular data set is all the characters from Game of Thrones, and the links are their interactions in the show. And this graph library supports the what they call a dot format, where it has a list of enums of basic shapes like diamond, like octagons, or double circles, things like that for each node. And I basically did a copy of the scatter plot layer, and all these shapes are created in the shader. And also, the crazy thing is, when you hover over it, because the layer knows when picking event happens, it is under the hood running transform feedback that is testing the relationships between the nodes through the edge list. So it's doing a depth test. It's right now, all the orange here are 1 degree away from the node that I'm hovering over, and the light yellow are 2 degrees away. And this is all done on the GPU and never left the GPU. So we're running an transform feedback to figure out the correct color for each node based on its distance to the currently hovered object, and we're passing that instead of the default color to that node layer to recolor all the nodes. If you have worked with very complicated large graphs, it's actually it actually takes a long time if you want to do the same thing on CPU, because it's single threaded, and you basically block the UI while you're trying to figure it out. So I will link to this repo on Slack channel, so you can see how the crazy gymnastics work under the hood. But these are the kind of things that I'm doing in the real world, using custom layers to solve a real problem. The sky is the limit. And as I said yesterday, like, it is very important to the deck.gl project that we keep everything highly customizable and well documented. So you can go as high or low level as you want. You feel comfortable with in the stack, and everything you can write your own version.